Hello friends, today we will learn modified Euler's method. In the previous video, we have learned about the Eulers method. Myself, Mr. P.S. Chogule from Department of Mechanical Engineering, SIT COE, Yadrao. So as you know, in the Eulers method, we need to find the approximate value of y1. Now see here, this one is the error which is somewhat bigger. Now we need to minimize this error, and this is the basic motto behind this modified Euler's formula. So how to reduce this error? So consider the distance between x0 and x1. We will consider it as the step size is of 2h, which ultimately means x1 is equal to x0 plus 2h. Now let us find the intermediate point xi in such a way that x0 plus h is equal to xi, and at this point, if we want to find the value of y intermediate, it will be at this place. Now by using the Euler's formula, we can find this value, this approximate value of yi1, which is equal to y0, means the previous value of y, plus h, which is the step size, into f of x0 y0, means in the function we need to put the values of x0 and y0. But the actual value of yi is somewhat at the different place on the curve here. So this will be the error, and now our task is to reduce this error, since we don't have the value of yi. So how to reduce it? By Euler's formula, what I have to do, I need to draw a tangent from yi1, so that I will get the value of y1. So if I draw the tangent from here itself, the error will get reduced at this level. So previously the error was this one, and now if I use the second step, the error will get reduced. But what I have to do, I need to draw the tangent from yi itself, so that the error will get reduced at this level. See, means error is get reduced, and what we have to do mathematically, we need to draw this tangent, so that we will get reduced error. So how to find this yi? Because we are having only the yi1 value, and now we need to find out the value yi. So for that, we have predicted the value yi1 instead of yi. We have predicted this value by means of Euler's method. That's why we call this formula as a predictor formula. Now the yi new, I can find out yi new because we are having the two tangents here. See, yellow tangent and this one is the blue tangent. Now if I make the average of the slopes of these two tangents, then I will get one approximate or better approximate value of yi. Remember that we are not having the value of yi, we are having the value of yi1. Now we need to reduce this error or get the better approximate value of yi. So for that, I will use this formula by taking the two slopes, slope at x0 y0, slope at x0 y0 from this tangent, and slope at x0 plus h, means xi and yi. xi, yi, this one slope I have to take. But since we are not having the value of yi, so that's why I will use this formula yi1, which is equal to y0, the previous value of y, plus h into bracket. Instead of taking a single slope, I will take here two slopes, and mean of these slopes divided by 2, right? So but still we don't have the value of yi, so instead of taking yi, I will take here the value yi1. So we will get the better approximate value of yi1, which we called yi1 new, which is in between these 2 points. It may be somewhat here. Now still yi1 new is not equal to yi, so for that I will do one more time this iteration yi2 new, and for that I will take one more time y0 plus h by 2 into bracket. Now here I will take the new value of yi, and since we have corrected this predictor formula to get error reduced, so that we called it as corrector formula. So similarly we can do the number of iterations to get the value of better yi1. It may be yi2, 3, 4, 5, 6 likewise, but we are here only, remember that. It is not like in a Euler's formula. In Euler's formula we will find the value of y at next x, but in modified Euler formula we have to calculate the value of yi only, but by number of iterations. At the particular xi only we will get the better approximate value of yi1. So in general, if I write here yi2, the second iteration will be in this form. Then in the third iteration I have to take the value of yi2 new. Here it is yi2 new. All other the terms which are constant, only I need to change the value of y. Similarly, I can write for yin, the nth iteration, which is of y0 plus h by 2 into bracket f of x0 y0, the slope of first tangent, plus the f of x0 h plus y n minus 1 I new, means the second tangent. We have to take the average of two slopes for the corrector formula. So in that case, this highlighted portion is of mean slope. This one is the first slope, second slope, and divided by 2, which means we can consider it as mean slope. So in general I can write here yin new is equal to y0 plus h into bracket mean slope. So while calculating by using modified Euler's formula, we need to remember something, and these are the things to remember. First, this is a two-step formula only. That ultimately means n is equal to 2. While calculating h, we need to have the value of n, which is equal to 2 in this case. So when h is not given, find h with n is equal to 2. By putting n is equal to 2, you can easily find out the value of h. Second thing, when h is given and equal to x means the value of y at particular x we need to find out, and if they given h which is equal to the value of x, then it is only one step formula. While we solve the examples, you will get clear idea about all these things. Just try to understand it. Then the third is the when h is given and it is not equal to or other than x, then the value will be, or the you need to solve this problem with the 2 steps only. So remember these points. So let's move forward towards the example. Here it is the example. Solve the differential equation dy by dx is equal to y plus e raised to x using second order Runge-Kutta method, that ultimately means the modified Euler's method. Sometimes they may call it as second order Runge-Kutta method directly, but remember that the first order Runge-Kutta method is nothing but Euler's method, and second order Runge-Kutta method is nothing but modified Euler's method. So under the boundary condition y0 is equal to 0, find y at x is equal to 0.2. Now here they have not given the value of h, so we will again go to this slide. Now see, when h is not given, you need to find h with n is equal to 2. So in that case, what we have to do, so I will write here dy upon dx is equal to f of xy is equal to the function y plus e raised to x. Now as step size is not given, we have to take here n is equal to 2. You are not allowed to take here n is equal to 4, 6 or any other value than the 2, because since they have not given the value of h, so you have to solve this with the 2-step formula. Now we can find the value of h by putting the value of x and x0. So the value of x is of 0.2 and value of x0 is equal to 0. So by putting these, we will get h is equal to 0.1. So now to solve this formula, I will use the tabular form. So in that, you have to add the mean slope column. All other are the same columns. In Euler's method, we are using 4 columns, but in modified Euler's method, we need to use the 5 columns. The first one, which is of x, second one y, third one f of xy, fourth one, which is the mean slope, and by that we will get the new approximate value of y. Now here is the basic conditions or initial condition, which is x0 is equal to 0, y0 is equal to 0. By putting these two values of x and y in equation, we will get the value of f of x0, y0. Now in this case, only one slope is there. I am not talking about the one number, I am talking about the slopes. Here only one slope, x at x0, y0, only one slope we are having. That's why we need to keep blank the mean slope. So according to the predictor formula or Euler's formula, I can find out the value of y1, which is equal to y0 plus h into slope of at x0, y0. So y0 is equal to 0 plus h is equal to 0.1 into f of x0, y0 is equal to 1. If I put all these values, I will get y1, which is equal to 0.05.